So for polar bonds, the main things you want to look for, I'll show you right here. So this is a chart of electronegativities. Notice the metals are all quite low, right? Hydrogen's 2.1, but all these metals are very low. And then notice up here in this corner is our high electronegativity. So these are the atoms that we want to keep track of right here. These are going to make our polar bonds, okay? So all these red ones, very electronegative, okay? So what I want you to pay attention to, so we have N, O, F, and Cl. So if you see N, O, actually let's do oxygen at the top. That's going to be the most prominent one. So O, N, F, or Cl. If you have a hydrogen or a carbon attached to these, right? So like a hydrogen, or even like OC, so oxygen and carbon, you know, fluorine and carbon, Cl and carbon. If you see bonds that look like this, right, that have any of these chemicals, right, oxygen, nitrogen, fluorine, chlorine, typically these are going to make our polar bonds. So all of these bonds here would be polar. I don't remember if N and C make a polar bond. That's getting really close, right? So N is 3, C is 2.5. So N and Cl are cutting it close. But they might be slightly polar, okay? All right, so again, this chart tells us that these are the main electronegative ones. So by the way, in these bonds, which ones would be the partial negative and which would be the partial positive? Well, remember that these ones here are the ones that are going to be pulling the electrons in. That means the other ones are losing electrons. So if we go back here, right, O is going to be slightly negative and H would be slightly positive. N would be slightly negative, H would be slightly positive, right? Again, there's no magic here. It's just that these are the electronegative atoms, so they pull on those electrons, right? F, again, is more than carbon, right? And then what if we wanted to know if something's polar, ionic, or nonpolar? Well, it depends on how big the electronegativity difference is. So all the compounds we just looked at are polar covalent, because if you look at their difference, it'd be 0.5 to 2.0, right? So what do we mean by that? Well, let's look at oxygen and hydrogen. So oxygen is 3.5. So oxygen has a 3.5 negativity. Hydrogen has 2.1. So when we subtract those numbers, we get a difference of 1.4, right? That's our electronegativity difference. That's basically telling you how strong they are. So like oxygen, right, is 3.5 strength, hydrogen is 2.1. So there's a 1.4 difference. And if we look down here, anything between 0.5 and 2 is considered polar covalent. So that's why this is a polar bond, right? Let's look at one more. Let's look at, let's go back and look at that C and H bond, right? Again, this ends up being a really important molecule. So we just looked at H, and it was 2.1. And then we're going to subtract that from carbon, which I don't remember off the top of my head, 2.5 for carbon. So if we look here, that ends up being a 0.4 difference. Look how close in strength they are. So let's look at the chart again. Is 0.4 a big deal? 0.4 would be in here, right? So non-polar, right? That's what makes this a non-polar bond, okay? So we want to look at those electronegativity differences. All right, let's see. If we look here, what do these electronegativity differences in covalent tell us? Well, our nonpolar, right, small difference in electronegativity. So these are our nonpolar molecules, right? So that's our gases like O2 and N2 or our CH bonds. Those tend to be gases at room temperature, okay? They tend to have low melting and boiling points, right? Because they're not attracted to each other. They don't have these strong attractions from those charges. So it makes sense that they freely form as a gas and they have low melting and boiling points and so on, right? Our polar covalent, there's a big range here. So towards this side of the spectrum, you'll get more gases and liquids that boil really easily. Towards this side of the spectrum, really big difference in strength. You'll get your solids or liquids that boil after you heat them up a lot. So these are moderate melting and boiling points, medium. And then anything ionic, this chart says greater than 1.7. I've seen more charts say greater than 2. So we'll say greater than 2 for ionic there. But anything greater than 2 is pretty much always a solid. There's really strong attractions because there's a really strong positive and negative charges there. Again, think back to the magnets that we looked at the beginning, right? The stronger the magnets, the stronger the attraction, the harder it is to separate them, so more likely to be a solid, right? So nonpolar, gas, low melting and boiling point. In the middle, we have our polar covalent, which can be a wide range, but typically more on the liquid side. And then ionic bonds tend to be solids. Okay, so let's look at a couple more examples here. So HCl, notice our electronegativities are written for us, 2.1 and 3.0. So our difference then would be 0.9, that's polar covalent. And then notice where they drew the charges, right? Hydrogen's positive because it has lower strength at pulling electrons, so it becomes a little bit positive. Chlorine is grabbing the electrons and pulling them closer this way, not taking them completely, but pulling them closer, so it gets this partial negative charge, right? So if we had another HCl, right, that would also be partially positive, partially negative, and so you'd have this little bit of attraction there, right? And so they're attracted to each other, so this would be like most likely a liquid, or maybe a very low melting point solid. Okay, water, really important molecule. Here's the other important part, is the shape. We'll talk about that now with water, and then we'll look at CO2. Okay, so with water, the electronegativity difference is 1.4. This is definitely polar covalent. And then let's just take a look at the shape here of these bonds. So if we draw our oxygen, remember, right, we have 2 lone pairs on oxygen, and then the 2 hydrogens come off of it. So we have 2 bonding groups, 2 lone pairs. So remember that this is called bent, right? And then remember the force, we can show the force of the electrons being pulled. So we know they're being pulled from the hydrogen to the oxygen with about 1.4 strength, and that's happening here and here, 1.4. And so we can see that we'll end up with some negative charge on oxygen, and then each of these hydrogens will be a little bit positively charged, okay? And it's because those bonds are both pulling in the same direction. Let's compare this with CO2 real quick before we move on. So CO2 also has oxygen, but it also has carbon, okay? And carbon was, what was it, 2.5, I think? Yeah, carbon was 2.5 electronegativity, right? So let's draw CO2 real quick. So CO2 would be this, and then remember carbon makes double bonds with the oxygen. So this is a linear shape, by the way, right? Because it has 2 bonding groups and no lone pairs. And then let's go and draw our force arrow. So our force arrow is going to be going from, so carbon is lower and weaker, oxygen is stronger. So the force arrow is going to be pulling the electrons this way towards the oxygen. And then the difference is 1.0, right? So 3.5 minus 2.5. So you might think that carbon dioxide's polar, but what do we see over here? There's another one pulling it this way with the exact same strength. And so if you remember from physics, if you have 2 forces in opposite directions, and they're the same strength, they'll cancel out, right? So what ends up happening is CO2 does have a polar bond between the C and the O, but because it has another one pulling the electrons in the opposite direction with the same strength, it ends up canceling out. So CO2 is non-polar because of that. So it does have a polar bond, but the shape prevents it from being polar. It's symmetrical, so the forces cancel out. So CO2 ends up being a gas, of course, right? We've heard that before. CO2 is a gas that floats around in our atmosphere. Low intermolecular force, and so really low boiling and melting point. This is, again, reviewing, right? So we can see that if you have HH, the electron cloud is shared evenly. ClCl, the electron cloud is shared evenly. But remember, chlorine is one of those electronegative atoms. So when you bond H and Cl together, you get a lot of electrons shifted this way and a little bit less there. So how would we draw the positives and negatives? Well, the electrons are leaving this spot, so it becomes more positive. Electrons are coming over here, so it's more negative, right? So, and then we have those positive nuclei in the center. Okay, so that's polar covalent, HCl. Let's do ethanol real quick. So ethanol is C, okay, 3 H's, and then OH. Okay, so, and then there's H's here. So there's a lot of bonds here, but if you look at the shortcuts, what did I say about CH bonds? These are all nonpolar. CC is of course nonpolar. They're exactly the same element. CO is very slightly polar, and OH is polar. So this molecule has a lot of nonpolar bonds, but then it has this little spot here where we have some polarity. Where would the charges go? So you should recognize oxygen is that strong one and hydrogen is weak. So we should expect to see a little bit, again, this symbol means a little bit, of negative here and a little bit of positive here, okay? So when this runs into another CH molecule, right, another ethanol molecule, this oxygen can hit one of the hydrogens on the other one, and this hydrogen can hit one of the other ones, and it'll kind of stack up opposite ways. Let me go ahead and show you that actually real quick. So if there was another ethanol molecule, it would end up being something like this. And again, so there'd be a little bit of positive here and a little bit of negative here, and so you would get a little bit of attraction between these two molecules, and they would kind of want to stick together a little bit. So there's some force attracting these two molecules together. So ethanol, of course, is a liquid, right? This is alcohol. It's the chemical in beer and vodka and wine. So of course, it's a liquid. So it has medium attraction. It's a polar molecule. Okay, so that's like the idea behind polar molecules, all right? So the key part is that you understand the electrons are not being shared equally. This creates some positive and some negative. The negative is on the side that's more electronegative, stronger at pulling electrons. Anything that's the same is going to be nonpolar. Anything that has a big difference is going to be polar. Anything that has a really big difference, metal and nonmetal, is going to be ionic. So tend to be gases, liquids, solids kind of in the middle there, but liquids most of the time. Then ionic, pretty much always solid. So low molecular forces, medium intermolecular forces, very, very high. And then just real quick, make sure you know these examples here. Make sure you know that anything that's bonded to itself is going to be nonpolar, and then CHs are considered the nonpolar. For polar, just remember these examples here. So any OH, NH, FH, CLH, OC, and then FC. Those are going to be your polar bonds, right? So that's what you're looking for in your molecules. Okay? All right, that's pretty much it.